An insurance company experiences a crisis following a severe storm. The crisis exposes critical flaws in the company's existing database system. Database queries are significantly slow, hindering timely information retrieval. Data inconsistencies within the system lead to unreliable information. These issues complicate the process of identifying affected policyholders. Accurate damage assessment is also impeded by the database's shortcomings. The database is failing to provide answers to fundamental questions. These questions include ownership, location, and insurance details. Inconsistencies in naming conventions contribute to the problem. Inaccurate addresses further complicate data retrieval. Risk objects are not properly linked or associated within the database. These issues collectively hinder the database's overall functionality and reliability. A critical request for active policy data arises from the CFO. The request specifies a regional scope and a tight deadline of noon. The existing SQL query demonstrates poor performance. This poor performance highlights database inefficiencies. The situation underscores the urgent need for a database overhaul. A database overhaul is necessary to meet critical data demands efficiently. The initial stage in database design involves modeling key entities. One core entity is party, representing individuals or organizations. Contact methods are modeled to include email addresses and phone numbers. Addresses are designed to be time-aware, tracking changes over time. Policy is another key entity, incorporating policy version for tracking changes. Risk objects, such as vehicles or properties, are also modeled as entities. Database design implements roles such as insured, broker, and underwriter as structured relations. This structured approach replaces unstructured text for defining roles. Implementing roles as relations ensures data integrity and consistency. The database supports recursion to effectively manage broker hierarchies. Recursion allows for representing complex relationships between brokers and their sub-brokers. This hierarchical representation facilitates efficient querying and reporting on broker networks. Effective database design avoids common anti-patterns to ensure optimal performance. One such anti-pattern is the use of CSV IDs, which can compromise data integrity. Another is relying solely on code to define relationships between data entities. Adhering to best practices enhances both data integrity and query efficiency. The database is optimized for rapid data retrieval. Users can quickly access a customer's active auto policy details. The system efficiently displays the vehicle identification number, VIN, associated with a policy. The database supports listing all policies linked to risk addresses in a defined area. This capability enhances risk assessment and management. Improved query speed contributes to operational efficiency. A normalized database is crucial for smooth business operations. It ensures data behaves predictably, aiding in efficient data management. Predictable data behavior simplifies data retrieval and manipulation. Normalized database facilitate effective auditing process. Auditors can perform their tasks more efficiently with structured data. Overall, normalization enhances data integrity and usability for various stakeholders. Storing JSON data in a single table column is a common but suboptimal approach. This method often results in data that is difficult to read and interpret. Searching and filtering become cumbersome due to the unstructured nature within the column. Generating reports from this type of data storage is also significantly challenging. The shoebox JSON approach involves manual extraction of information. This manual process increases the risk of fraudulent activities. Data duplication is more likely due to the lack of automated checks. Meaningful information requires extensive manual digging and validation. An ORM, Object Relational Mapper, is used to create a policy class. The policy class includes attributes such as policy number and holder name. The ORM aims to simplify database interactions by mapping objects to relational data. However, the ORM can sometimes hide underlying issues like broken links. It may also obscure the true relationships between different data entities. This abstraction can lead to unforeseen problems and complexities in the long run. Deleting a policyholder in an ORM system can trigger unintended consequences. This action may lead to the automatic deletion of all policies associated with that policyholder. This behavior indicates a lack of referential integrity within the ORM design. Referential integrity ensures relationships between tables are maintained during data operations. A novice data handler uses comma-separated IDs for linking customer data to policy information. This method involves embedding multiple IDs within a single field, separated by commas. The use of comma-separated IDs makes standard database joins impossible. Consequently, this hinders effective data analysis and reporting capabilities. The CSV ID approach involves managing data relationships using identifiers in CSV files. This method is analogous to listing multiple phone numbers on a sticky note. The system relies on correctly interpreting the relationships between these IDs. This approach can be prone to errors due to its simplicity and lack of explicit relationship definitions. The scenario involves an incorrect data modeling approach. Specifically, it addresses the misrepresentation of one-to-many relationships. The error lies in using a single column with CSV text to link customers to multiple policies. This method incorrectly embeds multiple values within a single field. A relational database is designed to handle one-to-many relationships using separate tables. Using CSV text in a column violates database normalization principles. One-to-many confusion violates database normalization principles. It hinders the proper implementation of foreign key constraints. This approach degrades performance during join operations. It also complicates historical data analysis. The database design incorrectly duplicates address columns in a party table. This approach attempts to represent a many-to-many relationship directly within the table. The correct method involves utilizing a junction table to properly manage the relationship. Duplicating columns leads to data redundancy and potential inconsistencies. A junction table ensures data integrity and efficient relationship management between entities. This design approach is flawed due to a lack of crucial information regarding usage and roles. The absence of time validity considerations further undermines its effectiveness. Arbitrary limits imposed on the design compromise both data integrity and overall flexibility. These shortcomings collectively render the design unsuitable for robust and adaptable applications. The scene illustrates a misunderstanding of how to handle hierarchical data. The incorrect approach involves creating separate database tables for each level of a broker hierarchy. This method leads to a rigid and unscalable database design. It becomes difficult to manage and query data across different levels. A more appropriate solution would involve a single table with a self-referencing foreign key. This allows for a flexible representation of the hierarchical structure. A rigid schema can lead to inefficient and complex queries. These complex queries can be computationally expensive and slow. A self-referencing party tree offers a potential solution. This alternative structure aims to simplify data relationships and improve query performance. A team convenes in a war room setting to address database design considerations. Whiteboards are utilized as a collaborative tool for visualizing and planning the database structure. Coffee is present, indicating a potentially lengthy and detailed discussion. Sample CSV files serve as practical examples for informing the design process. The primary principle is to allow data to reveal its inherent relationships. This approach avoids preconceived notions that may bias design. Previous design attempts may have failed due to imposing structures on the data. Data-driven relationships ensure a more accurate and organic representation. Database normalization is the process of organizing data to reduce redundancy and improve data integrity. The database is structured into several tables: party, address, policy, policy version, risk object, and role. Each table is designed to store specific types of data, minimizing duplication. Foreign keys are used to establish relationships between these tables. This relational structure ensures that data can be efficiently accessed and maintained. Data normalization is a process that ensures data truth. It also ensures data integrity within a database. Normalization minimizes redundancy. Normalization improves data consistency. It simplifies data relationship. Link tables such as party, address, are designed for managing relations between entities. These tables are particularly useful for zero-to-many relationships. Link tables include usage columns to specify the nature of the relationship. They also incorporate valid from and valid to columns for time-aware tracking. This time awareness allows for historical tracking of relationships. The structure supports accurate and auditable relationship management over time. Recursion can be implemented using a party table structure. The party table includes a parent, party, id column to define hierarchical relationships. This structure allows for broker networks of varying depths. A recursive common table expression, CTE, can be used to traverse this hierarchy. The Ultra-3 NF Core represents a database design approach focused on high normalization. Normalization minimizes data redundancy and improves data integrity. This architecture employs thin services to interact with the highly normalized core. This design is considered an expert option for database implementation. Ultra-3 NF database design offers several key advantages. It ensures strong data integrity, minimizing redundancy and inconsistencies. Ultra 3NF supports flexible query capabilities, allowing for complex data retrieval. The design enhances audit friendliness, simplifying data tracking and compliance. CQRS Split involves separating the read and write operations for data management. A normalized write model, 3NF, is maintained for data integrity during write operations. Read-optimized projections are created as materialized views or star schemas. These projections are specifically designed to enhance read performance. This separation optimizes both data consistency and query efficiency. CQRS, or Command Query Responsibility Segregation, is an architectural pattern. CQRS separates read and write operations for data. A key advantage of CQRS is enhanced performance, especially for analytics. CQRS can also simplify complex analytical queries. However, CQRS introduces additional complexity in maintaining data consistency. Extra pipelines are required to synchronize data between the read and write sides. Document hybrid storage represents a third option for data management. It involves storing the core data in third normal form, 3NF, ensuring relational integrity. A document sidecar, often in JSON-B format, is attached to this core. This sidecar is designed to accommodate rare and unstructured attributes. This approach balances structured data with the flexibility of document storage. Document hybrid systems offer increased agility in data management. This agility is achieved without the need for frequent schema modifications. However, effective governance is crucial for document hybrid systems. Governance helps prevent uncontrolled data sprawl within the system. Without governance, the system can become disorganized and difficult to manage. Therefore, balancing agility with governance is key to successful implementation. The team is opting for a CQRS architecture split. The claims platform requires transactional correctness. Fast reporting is needed, especially during storm events. CQRS supports both transactional needs and reporting speed. CQRS enhances data integrity in OLTP systems by preventing phantom relationships. It enables low latency reads through the use of data projections. CQRS future-proofs analytics by avoiding the need to bloat OLTP tables. This separation ensures that analytical queries do not impact transactional performance. The architecture supports efficient data retrieval tailored for specific application needs. The CQRS pattern can be understood through a kitchen analogy. The tidy kitchen represents the normalized core data model. This core maintains data integrity and consistency. The warm buffet symbolizes readily available read models tailored for specific needs. DDL, or Data Definition Language, is used to define database schemas. The database schema includes reference tables. Reference tables store static or slowly changing data. DDL statements specify the structure of these reference tables. This includes column names, data types, and constraints. The lob table is designed to store information about lines of business. This table includes columns for lob, code, representing the line of business code. It also contains a name column, likely used to store the name or description of the line of business. The table structure facilitates the organization and retrieval of line of business-related data. An address table stores structured location information. The table includes a column for the street address. A separate column is designated for the city name. The table also contains a column for the region or state. Postal codes are stored in their own dedicated column. Finally, a column exists for the country code of the address. The party address table serves as an intermediary link between party and address entities. It establishes a many-to-many relationship between parties and their associated addresses. Columns include usage to specify the purpose of the address for the party. Temporal validity is maintained through valid, from, and valid to date fields. The database schema includes tables for managing products. A separate table is defined to handle policies. These tables are essential for organizing product and policy data. The script focuses on defining the structure of these tables. This involves specifying columns and data types for each table. A product table is created as part of the database design. The table includes a product ID column to uniquely identify each product. A lob code column is included, likely representing a line of business code. The table also contains a name column to store the product's name. This structure facilitates organized storage and retrieval of product information. A policy table is structured to store key policy information. The table includes a policy ID column for unique policy identification. A product ID column links each policy to a specific product. The policy number column stores the unique identifier for each policy. A holder party ID column identifies the policyholder. The policy version table stores different versions of policies. It includes a policy, version, ID column to uniquely identify each version. The policy, ID column links each version to its corresponding policy. Version, no indicates the specific version number of the policy. Effective, from, and effective to columns define the validity period of each policy version. The policy, version table contains data about different versions of policies. A generated column named is, active is included in this table. The is, active column indicates whether a specific policy version is currently in effect. This column automates the tracking of active policy versions. It simplifies identifying the current policy version among historical records. The script outlines the structure for tables representing various risk objects. These risk objects can include items such as cars. Risk objects also encompass properties like homes. The tables are designed to store and manage data related to these diverse risk objects. This structured approach facilitates efficient risk assessment and management. Each table contains specific attributes relevant to the corresponding risk object. The policy, risk, object table is designed to store data linking insurance policies to specific risks. It includes a risk, object, ID column, serving as a unique identifier for each risk object. The policy, version, ID column links each risk object to a specific version of an insurance policy. The risk type column categorizes the type of risk associated with the object. The VIN column stores the vehicle identification number, relevant for vehicle-related risks. Additional columns such as air code, postal code, and description provide further details about the risk object. The DDL script defines database tables related to roles. These roles include insured, representing individuals or entities covered by insurance. The script also defines the broker role, referring to intermediaries who facilitate insurance transactions. Additionally, the underwriter role is defined, representing entities that assess and assume insurance risks. Therefore, the DDL script establishes the structure for managing these key roles within the database. The policy role table is designed to store information about roles associated with policies. It includes a policy, role, ID column, serving as the primary identifier for each role entry. The policy, ID column, links each role to a specific policy within the system. A party, ID column identifies the party or entity associated with the role. The role type column specifies the type of role that the party holds in relation to the policy. Policy documents are stored separately for organized management. Notes related to the policies are also stored separately. Checksums are generated for each document to ensure data integrity. Embeddings, project vector, are created for semantic lookup capabilities. Semantic lookup enhances the ability to find relevant information. This system is designed to be RAG, Retrieval Augmented Generation, friendly. Change Data Capture, CDC, is employed to establish an audit trail. CDC also creates a topic for data lineage tracking. This topic is crucial for monitoring ML feature freshness. While 2JSON and PGLogical are common tools used for change data capture, these tools facilitate the extraction and propagation of data changes. Customer similarity vectors are generated as a key feature. Broker network graph features are also generated. These features are generated using recursive queries. Recursive queries allow for in-depth data analysis. The generated features are AI-ready for further processing. The core principle involves accurately representing truth within the OLTP system. This is achieved through the strategic use of keys to uniquely identify data entities. Data types are also crucial for ensuring the integrity and validity of the information stored. Incorporating time-related data provides a temporal dimension to the modeled truth. Effectively modeling truth using keys, types, and time is essential for a robust OLTP core. Business speed is enhanced through the utilization of read models. Read models are also known as views or materializations. These models provide optimized data structures for specific query patterns. By pre-computing and storing data in a readily accessible format, read models minimize query processing time. This approach allows for faster retrieval of information, thus serving business speed requirements. In crisis management, integrity is paramount. Speed is secondary to maintaining ethical standards. When integrity and speed are combined, they lead to effective crisis resolution. Prioritizing integrity ensures trust and long-term success during challenging times. Data normalization is a fundamental process in database design. Its primary goal is to eliminate data redundancy within the database. Normalization ensures that each piece of data is stored only once. This process enhances data consistency and integrity across the database. Foreign keys are used to establish and enforce relationships between tables in a database. They ensure data integrity by requiring that a value in one table must exist in another. This mechanism prevents the creation of orphaned records, which are records that reference non-existent data. By maintaining referential integrity, foreign keys help keep the database consistent and reliable. Junction tables are crucial for managing many-to-many relationships in databases. They provide a structured way to link entities that have multiple connections with each other. Each row in a junction table represents a single link between two entities. This approach ensures clarity and efficiency in relational database design. Junction tables prevent data redundancy and maintain data integrity across related tables. Time validity integration in database design enables tracking changes. This approach facilitates the maintenance of historical data within the database. Time-aware design ensures that data is associated with specific time intervals. This allows for querying the state of the data at any point in time. Implementing time validity is crucial for applications requiring audit trails or historical analysis. Recursion offers a streamlined approach to representing hierarchical data structures. It simplifies the process of defining and manipulating complex relationships within data. This simplification leads to more efficient querying of hierarchical data. Recursion also enhances the overall management of these complex data structures. The result is a more scalable and maintainable system for handling hierarchical information. CSV-IDs can lead to improperly defined relationships within a dataset. These poorly defined relationships can hinder efficient querying. Avoiding CSV-ID ensure data integrity. Maintaining data integrity allows for accurate analysis. Accurate analysis is crucial for informed decision-making. Therefore, avoiding CSV-IDs is a best practice for data management. Storing data in a single JSON column can create challenges for data querying. Analyzing data becomes more complex due to the nested structure within JSON. Inconsistencies in data structure can arise when storing various JSON objects. These inconsistencies complicate data processing and standardization efforts. Efficient data management requires careful consideration of JSON storage implications. ORMs, or Object Relational Mappers, are tools that simplify database interactions. However, ORMs can sometimes obscure the underlying complexities of database operations. This abstraction may lead to a lack of awareness regarding potential database issues. ORMs might not always provide the most efficient way to represent data. The data representation provided by an ORM may not be entirely accurate in all cases. Therefore, developers should be aware of the limitations when using ORMs. Normalization is a core database design principle. It is primarily used to prevent data anomalies within a database. Normalization also improves the overall quality of the data. By reducing redundancy and dependency, normalization ensures data integrity and consistency. Data integrity is crucial for maintaining accuracy within a database. It ensures the reliability of the information stored. Maintaining data integrity is essential. Data integrity confirms data accuracy. It also ensures data reliability. A well-designed database schema is crucial for optimizing query performance. Effective schema design enables faster data retrieval. Improved query performance leads to more efficient data access. Optimized queries reduce the time required to obtain necessary information. Scalable database design is engineered to handle increasing data volumes. It also accommodates growing user loads without performance degradation. The primary goal is to maintain optimal efficiency as the system expands. This involves strategies for data partitioning and distribution. Effective indexing and query optimization are also crucial components. Scalability ensures the database remains responsive and reliable over time. Protecting sensitive data requires implementing appropriate security measures. These measures safeguard data stored within the database. Effective security protocols are essential for maintaining data integrity. Security measures also ensure the confidentiality of stored information. Robust security protocols are critical for preventing unauthorized access. Regular security audits help identify and address potential vulnerabilities. Regular data backups are crucial for protecting against data loss. A well-defined recovery plan ensures data availability after a disaster. These measures are essential for business continuity. Effective backup and recovery strategies minimize downtime and data loss. Monitoring database performance is crucial for maintaining system health. Effective monitoring helps in identifying potential issues proactively. Addressing these issues prevents negative impacts on users. This includes tracking key metrics like query response time. It also involves monitoring resource utilization, such as CPU and memory. Regular monitoring ensures optimal database operation and reliability. Database indexes are crucial for enhancing the speed of data retrieval. Appropriate use of indexes significantly improves query performance. Indexes enable the database system to quickly locate specific rows. This rapid location avoids the need for full table scans. Consequently, query execution times are reduced, leading to more efficient database operations. Partitioning divides large tables into smaller segments. This division enhances query performance. Partitioning simplifies data management tasks. Smaller chunks of data are more manageable. A data warehouse is a centralized repository. It stores historical data from various sources. The data is structured for analysis and reporting. This enables better decision-making based on trends. Business intelligence tools analyze data stored in databases. These tools generate reports to provide insights into business performance. Dashboards are also created to visualize key performance indicators. The reports and dashboards aid in understanding business trends and making informed decisions. Data governance policies are crucial for maintaining data integrity. These policies establish guidelines for data quality. They also ensure consistency across different data sources. Compliance with regulatory requirements is a key aspect of data governance. Well-defined procedures support the effective implementation of these policies. Effective data governance enhances trust and reliability in data-driven decision-making. Continuous review is essential for database design. Continuous improvement is essential for database implementation. These practices ensure the database meets evolving business needs. Regular reviews help identify areas for optimization. Improvements ensure the database remains efficient and relevant.